This seminar is about castings and test block properties, and we wanted to do it because there's such a fundamental misunderstanding of what it means, what we're trying to accomplish when we actually pull test bars from a heat of steel. And the common idea that design engineers would like to have true, but it's not true, that the materials that they buy from any supplier have high properties everywhere in every direction, so that they can design with confidence using their models. But that's not true of any real materials. Real materials have different properties in different locations, depending on their processing and on physics and everything else. So the real challenge is knowing enough about the materials and the manufacturing process to have confidence that the design you use has and the material you use has the properties that you need, where you need them, when you need them. So to start out, I should clarify that we're unusual in North America because we actually require a tensile test from virtually every heat of steel. If you order using ASTM material requirements for steel, then we're required to do a tensile test with every heat that we make. And for some reason, we've evolved now where people believe that I'm doing that tensile test to guarantee to you that you have those tensile properties everywhere in the casting. And that's fundamentally a misconception. The reason we do a tensile test is because in 1920 or 1930, every steel maker, including steel foundries, had a laboratory like the picture you see. And to do a chemical analysis required that guy with the glasses to actually individually for each element analyze it using titration, using wet chemical methods. And in fact, he would do that for all of the required elements. And so I might not know for a week what the chemical composition of my heat was. In fact, we had melting people who were really clever, and they could tell from taking a piece of steel and grinding it by seeing the sparks that shot out of it about what carbon content it had. And we could identify how hard the steel was by using different files and different metals to see which one scratched the steel, because we just didn't have all the analytical tools that we have now. And because at this time in the 20s and 30s, we didn't have the chemical analysis, how did I know that the steel that I was sending you wasn't contaminated with something like tin or lead that I wasn't analyzing for? And the way that I made sure that the steel that I sold you was what you expected that steel to be able to do, what it was capable of doing, was to check each heat of steel with a tensile test, because a tensile test was fast, quick, and cheap, and allowed me to demonstrate that we got the properties out of that heat of steel that I expected. And so the ASTM tensile test is a test of the steel heat, not a test of the products that I sell you. We see this even today. ASTM A6, the A committee is the steel committee. It was the first committee formed by ASTM in the 1800s, late 1800s. The A standards are sequentially numbered. So A6 is the sixth standard, the number 6 standard that was ever written by ASTM. That standard is the oldest still active standard. So that is still in the latest book. And in that standard, to clarify this, there is an Appendix X2, and you can see in bold here that the procedures, the test procedures for tensile testing, are not intended to define the upper and lower limits of tensile properties at all possible test locations within the heat of steel. And the first sentence says it's to determine the characteristics of the heat of steel for the requirements of the specification, not to provide tensile test results that you can use guaranteed every place in the product. Now, in steel castings, we pour a special keel block design that's designed so that it's sound. These legs are sound, and then we cut the legs off and heat treat them the way we heat treat the casting. And that is the way we demonstrate our conformance to the ASTM specification. So if you order an ASTM grade 216 WCB, this is where I take the test material from. And all of the steel casting grades are either referred to ASTM A703 for pressure containing more critical parts or A781 for general use. And you can see we have basically the same note in the ASTM casting standard that they do in the plate and bar standards. The tension test requirements are intended only to characterize the tensile properties of the heat for determination of conformance to the requirements of the specification. They're not intended to tell you all the tensile properties everywhere. So you get a casting and you cut it up and you take tensile specimens out of it. Some of them will be higher than the properties we report. Some of them are likely to be lower, especially if you take them from the center line where there's some segregation and porosity. And so it is incumbent on designers and engineers to use sound engineering judgment when using tension test results. And so we're qualifying the steel we made, not the casting. We're showing you that the steel we poured in that hole had the properties we expected, and so we would anticipate the properties of the product will meet your expectations. So the reported properties can be used to assure the casting has the properties expected, but that doesn't mean that you'll get those tension properties everywhere. And so historically, we would print information in our handbook, and this note is still in the current ASTM standard. So we were talking this morning about the fact that we need to get our ASTM buddies to upgrade because we're on the 6th edition and we actually can upgrade it online. So we need to change this note, but we actually have information to give you some indication of how you deal with the difference between the reported tensile properties and what you'd expect in the casting. We actually have on our website a whole write-up on test coupons that you might find to be useful. So this is what that section looks like, and there are a number of things that show how the section size affects the properties. So in a cast carbon steel, the yield strength is around 40 KSI, which means that, for example, in the boiler code, you use 20 KSI. 40 years ago, when I started my engineering career, I can tell you that the big producers like Caterpillar and John Deere were still breaking parts when they made a new design. They had test labs where they actually verified that the part would meet the requirements. Even today, when you're making crane hooks and crane hardware, they do proof testing to prove that the new designs and the existing products meet the requirement. And so at that time, everybody did the internal testing to show they actually had the properties. Now we're in a model-based environment where you want to know the properties every place in the casting, and you'd like to have a single value everywhere. And unfortunately, that's not the way the world works. So if I look at an alloyed steel, in small sections, I get fairly uniform properties. But because of the thermal conductivity of the steel, I can't cool it fast enough in the center. So for a 6-inch section for an 8600 steel, you can see that the tension strength and the yield strength go down. But with that alloy steel, I'm still much stronger than I was with carbon steel. So in carbon steel in the center of the 6-inch section, I'm a little under 40 KSI. In 8600, I'm still over 80 KSI. So those alloyed steels still give me improved properties even when the heat treatment can't reach into the center. And of course, today you're not only concerned with strength, but also toughness. And so we have some information about the variation of toughness with section size and fatigue properties. Now, if you are making critical castings, things for the oil field, things for the Navy, then people want larger test blocks so that you can actually directly correlate. And so actually in ASTM A148, that is a specification that lets you order steels by properties, not alloy, and the foundry or the producer gets to decide what alloy to make. And so in this specification, it says if you're going to have a quenched and tempered steel casting and it's thicker than 3 inches, then you've got to meet the requirements with S15. S15 says you have to cast a separate test block that's big enough to emulate. So T is the thickness. So this says when T is over 3 inches, then I have to make a test block. And that test block, if it was 3 inches, would be 9 inches by 9 inches by 3 inches thick. And I would take the test at T over 4. Or 1/4 of the way to the center. T over 2, I'm in the center. The center is the last place to solidify typically, and so it has segregation and microporosity, and you don't load it normally because you have some bending moment, and so it's not particularly useful to know the properties in the center. The surface is going to have properties that look like the keel block because it cooled fast. And so T/4 is determined to be the most practical way of characterizing the properties of the casting with that section thickness. And so that's why we do a T/4 test. And we do it in a 3T by 3T by T section. Now, when I do that, when I call out S15, these test blocks are expensive. They get big fast, and they tell you what the properties are in the test block, not necessarily in the casting everywhere. And the S15 in paragraph 3.2 says when it's over 5 inches, you can just make it a 5-inch test block. So if you think about it, the A148 says if it's over 3 inches, I have to do a test block. But once it's over 5 inches, I use a 5-inch block. And that's because these things get big fast. A 3-inch test block is 70 pounds, and I have to put risers and gates on it, so it weighs over 150 pounds. So if I have a 1,000-pound induction furnace and you want a 3-inch test block, I'm using 15% of the heat to make the test block. A 5-inch test block is 700 pounds. And so you can see right away that you're going to chew up an awful lot of steel really fast if you want a special test block. But special test blocks can be really useful. So the test blocks separately do provide a real value. And the value they provide is if you make me qualify to make a separately cast test block, it means that I have the technical skills, the process disciplines, and the process capabilities to meet the properties you need in the section size of your casting. So if you ask me to make a test block, what you've proven is that I have the skill and the technology to meet the properties in a test block, and you assume, and correctly so, that that means I should have the technology to make a casting with those kinds of properties. If you have me do a cast test block with every heat, that shows that not only can I do it one time, but that I can do it every time, so that I have the process disciplines, the skill, and the capability to make those properties in each heat. So if you have a critical casting, a separately cast test block can be a useful guarantee that you're getting the properties with every heat. And if that part fails, it gives you documentation that the part was made correctly and had the properties you anticipated. But you have to recognize that separately cast test blocks get big fast. One of the other things that people will often do is say, I'll just add a chunk on to the casting and then I'll cut it off and get the tensile test from that chunk. And that can be a good and useful technique. But if you do this, and I'm worried about this section here, then what I'm really doing is I'm making a test block that shows me what the properties would have been here if I had not put the test block on. But putting the test block on means I'm going to have poor material out in this area right where I want good material. So generally, adding a block on needs to be done carefully, or you compromise the material in the casting where the test block is attached. So just in summary, if we look at casting properties versus test blocks, the mechanical tests and analysis are for the acceptance of the thing. They're done by the producer. They're not done by you. The mechanical properties taken from the castings can be used by me, the producer, to qualify the part, but you can't use them to reject the part. So if I don't have enough test material and I cut a chunk off your casting and weld material back on, I can use that on an expensive big casting to show that I met your properties. But if you take that same casting and cut it up and say that the properties are not in the casting, you cannot reject the part with those properties. Now, if you want to, you can always put anything in your purchase order you want, and you can tell me you're going to do that. And if I accept the order, then you have every right to require that when you cut the casting up in a certain location, you get the test properties. But that's a special requirement. That's not a normal ASTM requirement. In the same way, if you do a chemical analysis, in ASTM, it gives a table, in A703 and 781 that says that the specification becomes wider. So the check analysis is not to see that you get close to the heat analysis I report. The check analysis makes the specification wider so that my casting is still in spec, even if it doesn't meet the specification of the grade, as long as it meets the specification widened by the check analysis in Table 1. So this table is not for the variation from the heat analysis, it's from the variation from the specification itself. And what you should recognize is variation in properties and analysis occur in all steel products, not just castings. So with that, I think we're done. We've agonized over this. I remember talking to one of my colleagues that works for a large OEM, and he thought I ought to guarantee the properties in every casting. And I can tell you, we would be delighted to do that. That just means I have to saw up every casting and test it, which means you never get a product that you can actually use in service. But I can make products and test them and show that every product I made would have performed if you had used it. And so we really have to use our engineering skills and our confidence that our engineering skills and material understanding is good enough that our products will meet our performance expectations.